The year is 1918. The guns have fallen silent across the scarred landscapes of Europe, but a profound and unsettling lesson has been seared into the consciousness of every military strategist and engineer. The battlefields of Verdun and the Somme stand as grim, churned-up testaments to a single, inescapable truth. The era of relying solely on wheels for warfare has irrevocably ended. Standard trucks flounder helplessly in the primordial mud, their wheels spinning uselessly. The mighty tanks, for all their fearsome power, are mechanically fragile, prone to breakdowns and agonizingly slow. The new challenge is one of mobility across a nightmarish terrain that more closely resembles the cratered, barren surface of the moon than any European countryside. It is within this pressing dilemma that our story finds its beginning, not with a sudden, brilliant invention, but in the arduous exploration of a mechanical paradox, a fusion of two seemingly incompatible ideas that circumstance demanded must be made to work in concert. The conceptual seeds of the half-track were sown not on the battlefield, but in the royal garages of Russia. As early as 1911, a visionary French engineer named Adolphe Kegresse, serving Tsar Nicholas II, confronted the immense challenge of maintaining the Romanovs' mobility during the harsh Siberian winters. His innovative solution was both simple and revolutionary. He replaced the conventional rear axles and wheels of the imperial automobiles with a flexible, continuous rubber track system, while retaining the standard front wheels for steering. This hybrid configuration was not just a theoretical exercise, it proved remarkably effective in practice, allowing the vehicles to traverse deep snow and soft ground that would have immobilized any wheeled car. By 1919, the French automaker Citroën had acquired Kegresse's patents, further developing and commercializing the Kegresse Hinstand system. These early vehicles demonstrated conclusively that this hybrid approach could conquer terrains that were utterly impassable for purely wheeled vehicles. Yet, at this stage, the application was purely utilitarian, a means of overcoming nature's obstacles to get from one point to another. The thought of its military potential was still a distant glimmer. The 1920s ushered in a period of intense, if often quiet, military introspection. Planners analyzed the lessons of the Great War and began asking difficult, uncomfortable questions about the future of conflict. Tanks had proven their worth as breakthrough weapons, but their strategic utility was hamstrung by their glacial pace. A British Mark V tank, for instance, could manage only a ponderous 4 miles per hour on favorable terrain. Trucks offered speed on roads, but the moment a column was forced to leave the pavement, the entire advance risked grinding to a halt in the first patch of mud. Meanwhile, the infantry, the backbone of any army, still moved at a Napoleonic pace, marching on foot. This created an unsustainable disconnect. Armored spearheads could achieve a breakthrough, only to find themselves isolated and vulnerable, forced to wait for days as the supporting infantry trudged wearily behind. This tactical problem ignited a fire of innovation across the globe. The Germans, despite the crippling restrictions of the Versailles Treaty, were already clandestinely sketching designs and exploring concepts for future mechanized warfare. The Soviets, embracing industrialization, began their own extensive experiments with cross-country vehicles. Even the United States, which had employed tanks only sparingly in the recent conflict, initiated design and testing programs at facilities like the Rock Island Arsenal. The half-track emerged as the most promising solution to this mobility conundrum. Its appeal lay in a masterful engineering compromise. It offered approximately 70% of a tank's all-terrain capability while retaining about 80% of a truck's speed, reliability, and mechanical simplicity. The front wheels provided intuitive and effective steering without the need for the complex and maintenance-heavy track braking systems used on full-tracked vehicles. The rear tracks distributed the vehicle's weight over a much larger surface area, enabling it to float over mud, sand, and snow. Furthermore, because the drivetrain did not have to power all 4 corners with tracks, the entire vehicle was lighter, less expensive to produce, and far easier to maintain than a dedicated tank. In 1931, the U.S. Army tested a prototype known as the Cunningham T1. It was, in essence, a standard truck chassis with tracks crudely affixed to the rear. Its appearance was almost comical, yet its performance was undeniable. It confidently crossed trenches and navigated soft ground that would have completely swallowed a conventional truck. By the mid-1930s, the geopolitical climate was shifting from theoretical planning to urgent necessity. Germany was openly rearming, flouting the Versailles Treaty. Japan was pushing deep into China with mechanized columns. The Spanish Civil War, 1936-1939, became a bloody proving ground where all major powers observed the same brutal lesson. Modern, high-tempo warfare demanded that infantry keep pace with armor, and they needed to arrive at the battlefield ready for immediate combat, not exhausted from a long, footsore march. The half-track was no longer merely a clever mechanical curiosity. It was rapidly evolving into an operational necessity. Engineers in Detroit, Stuttgart, and Moscow were now in a race to solve a complex puzzle. How do you construct a machine that possesses the off-road prowess of a tank, the cargo capacity and speed of a truck, and the potential firepower of artillery, all while remaining affordable enough to be manufactured by the tens of thousands? The answer to this question would come to define the machines that would soon roll into Poland, race across the plains of France, struggle through the deserts of North Africa, and ultimately see service across half the globe. The era of the hybrid warrior was dawning. The American approach: philosophy of mass production. The American military-industrial complex approached the half-track challenge with a characteristic and overwhelming focus on mass production from the very outset. While European designers often crafted vehicles with a degree of artisanal care and technical refinement, American engineers at companies like the White Motor Company in Cleveland and Autocar in Pennsylvania were thinking in terms of vast assembly lines, standardized parts, and a production volume that could reach staggering levels. The tangible result of this philosophy was the M2 and M3 half-track family. These vehicles presented a facade of brutal, no-frills simplicity, but concealed beneath their angular, slab-sided steel bodies was a wealth of pragmatic and genuinely clever engineering. The heart of the American half-track was its power plant. White Motor Company selected the Hercules JXD, a rugged inline six-cylinder gasoline engine with a displacement of 386 cubic inches. This engine produced 147 horsepower at 2,800 RPM, a figure that may seem modest by contemporary standards, but its true virtue lay in its proven reliability, ease of manufacture, and straightforward maintenance. Mechanics who had trained on civilian commercial trucks were already intimately familiar with its design and operation, a crucial advantage for field repairs. The engine was mounted in a conventional truck-style position at the front, which simplified cooling and provided excellent accessibility for maintenance crews. On paved roads, the M3 could reach a respectable top speed of 45 miles per hour, which would drop to around 25 miles per hour during cross-country travel depending on the severity of the terrain. This performance envelope was precisely calibrated. It was fast enough to maintain pace with advancing tank columns, yet not so fast as to subject the 10 infantrymen in the rear compartment to an unbearably jarring and bone-rattling ride. The transmission system was where the White engineers truly demonstrated their expertise. They implemented a robust 4-speed manual gearbox, coupled with a 2-speed transfer case. This combination provided the driver with a total of 8 forward gears and 2 reverse gears. This wide range of gearing was essential for the vehicle's versatility, allowing it to crawl up steep 60% gradients in first gear, low range, or cruise efficiently on highways in fourth gear, high range. Power was delivered from the transmission to a standard front axle for the wheels, while a separate drive shaft ran rearward to power the track assembly. The front wheels handled primary steering duties in a conventional manner, but the vehicle also featured a clever secondary system. The driver had access to brake pedals that could independently slow one track or the other, enabling much tighter turns than the front wheels could achieve alone. Mastering this technique required skill, but an experienced driver could maneuver the vehicle with surprising agility, nearly pivoting it on the spot. The track system itself was a masterpiece of American pragmatism. Instead of employing the noisy, heavy, and pavement-destroying metal links used on tanks, the M2 and M3 utilized advanced rubber block tracks developed in collaboration with the Firestone Tire and Rubber Company. Each track was composed of a core of high-tensile steel cables around which durable rubber was vulcanized. Onto this rubber belt, 110 individual rubber blocks, each about 5 inches wide and scientifically shaped for optimal grip on various surfaces, were bonded. The advantages of this design were threefold. First, the rubber tracks were significantly quieter than metal ones, a critical factor for tactical stealth and unit communication. Second, they were far more durable on paved roads, preventing damage to infrastructure and exhibiting a much longer operational lifespan. Third, and perhaps most importantly, maintenance was simplified. If a section was damaged, individual rubber blocks could be replaced in the field without the need for heavy equipment or a complete track overhaul. The suspension utilized a modified vertical volute spring system. Essentially, large coil springs were mounted vertically behind each of the 4 road wheels on the track assembly. As the vehicle encountered obstacles, these springs compressed to absorb the shock. To claim the ride was comfortable would be a gross exaggeration. Traveling in the back of an M3 over rough terrain was often compared to being inside a tumbling cement mixer. However, the system was effective, incredibly simple to maintain and repair, and, most critically, it distributed the vehicle's 20,000-pound combat weight evenly, resulting in a ground pressure of approximately 10 pounds per square inch. For context, a fully loaded truck could exert ground pressure of 40 psi or more, which perfectly explains why trucks bogged down in mud while half-tracks could continue to advance. When the United States entered the war in December 1941, production escalated at an astonishing rate. The manufacturing plants of White Motor, Autocar, and Diamond T were soon churning out over 500 half-tracks per month by mid-1942, a figure that skyrocketed to 1,500 units per month by 1943. By the war's end in 1945, total production of all variants had surpassed 41,000 vehicles. This prodigious output was the ultimate expression of the American design genius. The M2 and M3 may not have been the most technically sophisticated or refined half-tracks in the world, but they were good enough, and they were available in overwhelming numbers precisely when and where the Allied armies needed them most. The German counterpoint, the pursuit of technical perfection. In stark contrast to the American philosophy of mass production, German military designers were driven by an obsession with technical perfection, often regardless of cost or manufacturing complexity. The Sonderkraftfahrzeug 251, Sd.Kfz 251, most commonly known as the Hanomag after its primary manufacturer, embodied this entirely opposing engineering ethos. Where the American motto was "good enough is good enough," the German imperative was that every component should be engineered to the absolute pinnacle of mechanical performance. This resulted in a half-track that was phenomenally capable in specific conditions, but notoriously complicated and resource-intensive to build. The core of the Sd.Kfz 251 was its power plant, a Maybach HL42 2KRM 6-cylinder gasoline engine that produced 100 horsepower, less than the American Hercules. However, the significance lay in its pedigree. Maybach was the same esteemed company that produced engines for Germany's formidable Panther and Tiger tanks. The HL42 was not a repurposed truck engine. It was meticulously designed from the ground up for tracked vehicles, with a particular emphasis on delivering high torque at low RPMs, which is essential for off-road mobility. This engine could propel the 8.5-ton vehicle to a road speed of 53 kilometers per hour, about 33 mph, actually making it faster on paved surfaces than the American M3, though its cross-country performance was broadly similar. German transmission engineering often bordered on over-engineering. The Sd.Kfz 251 was equipped with a Maybach VG28H preselector transmission, a complex unit offering 7 forward speeds and 3 reverse gears. This system allowed the driver to preselect the next gear using a small lever, and then, with a simple tap of the clutch pedal, a vacuum-assisted mechanism would execute the shift automatically. When functioning perfectly, this provided smoother and faster gear changes than a fully manual system. However, when it malfunctioned, which was not uncommon under harsh field conditions, repairs required highly specialized mechanics and scarce replacement parts, which could take weeks to arrive. This encapsulates the fundamental dichotomy of the German half-track. Technically superior in theory, but a logistical nightmare in practice. The track system further revealed the German design priority of ultimate performance over simplicity. Instead of rubber blocks, the Sd.Kfz 251 used narrow, all-metal track links, identical in concept to those on tanks, connected by hardened steel pins. These manganese steel tracks were incredibly robust and could withstand tremendous punishment, but they were also extremely loud, chewed up road surfaces, and demanded constant adjustment and maintenance to maintain proper tension. The most distinctive and most problematic feature of the German half-track was its interleaved road wheel suspension. While American half-tracks used a simple arrangement of 4 or 5 wheels per side, the Sd.Kfz 251 featured 7 overlapping and interleaved road wheels on each side. This intricate design, resembling a zigzag pattern when viewed from behind, distributed weight with exceptional evenness, further reduced ground pressure, and provided an uncommonly smooth and stable ride over rough ground. German soldiers who had experience with both their own Hanemags and captured American M3s consistently praised the superior comfort of the German suspension. The severe drawback, however, was a maintenance catastrophe. If an inner road wheel was damaged or simply needed replacement, mechanics were forced to remove several of the outer wheels first to gain access. In the muddy, icy conditions of the Eastern Front, this design became a death trap. Mud, snow, and slush would pack solidly between the tightly spaced wheels, freezing overnight into concrete hard blocks. Crews had to spend hours each morning, often in sub-zero temperatures and under fire, using hammers, pry bars, and even blowtorches to break the wheels free. A task that might take 15 minutes on an American M3 could consume half a day on a Hanemag. This manufacturing and maintenance complexity was reflected in the production numbers. Building an Sd.Kfz 251 required approximately 3,000 hours of skilled labor in 1940, compared to a mere 800 hours for an American M3. Throughout the entire war, Germany managed to produce only around 15,500 Sd.Kfz 251s, a formidable achievement given its industrial constraints, but less than half of the American output. The half-track, therefore, became a perfect symbol of the broader conflict. American quantity versus German quality, embodied in steel and rubber. The weapons platform, mounting artillery on an improvised chassis. The inherent versatility of the half-track inevitably led to a more audacious idea. What if these armored troop carriers could be transformed into mobile artillery platforms? The concept may seem reckless at first glance, but it addressed a critical tactical weakness of traditional artillery. Towed guns, whether pulled by trucks or horses, required lengthy setup and disassembly times. This made them highly vulnerable to enemy counter-battery fire, as they could not quickly displace after revealing their position. By mounting a gun directly onto a half-track's chassis, engineers created a new class of weapon, mobile firepower that could shoot and scoot, engaging the enemy and rapidly relocating to avoid retaliation. However, the engineering hurdles to achieving this were monumental. The primary and most immediate challenge was managing the colossal forces of recoil. Firing a 75mm field gun, for instance, generates a rearward force of approximately 15 tons in a fraction of a second. If this force is not properly managed, it will violently tear the gun from its mount, warp the vehicle's frame, or even flip the entire vehicle backward. American engineers, working on the M3 gun motor carriage in 1941, devised a multifaceted solution. They mounted a French 75mm gun onto a heavily reinforced pedestal that was welded directly to the vehicle's strongest structural members, the chassis frame itself, not just the thinner bodywork. They then incorporated large, hydraulic recoil cylinders that allowed the entire gun barrel to slide backward roughly 2 feet upon firing. This mechanism transformed the instantaneous, destructive shock of recoil into a longer, more manageable push, dissipating the energy over nearly a full second. However, Newton's third law of motion remained in full effect. For every action, there is an equal and opposite reaction. Even with an efficient recoil system, firing the gun would still rock the entire vehicle violently. The solution to this was the implementation of outriggers and spades. These were sturdy metal legs equipped with broad plates on their ends that were hydraulically or manually swung down from the sides and rear of the vehicle before a fire mission. The crew would drive the spade at the rear into the ground, effectively anchoring the half-track in place and transferring the recoil forces directly into the earth. The massive M12 gun motor carriage, which mounted a powerful 150cm howitzer on a lengthened M3 chassis, featured an enormous spade at the rear that was absolutely essential. Without it being securely embedded, firing the gun would shove the 26-ton vehicle backward several feet with each shot. The Germans adopted a slightly different tactical and engineering approach with variants like the Sd.Kfz 251-9, which mounted a short-barreled 75mm gun. Rather than creating a true, long-range artillery piece, they designed an assault gun. This vehicle was intended to advance directly with infantry squads, using its cannon to blast enemy strongpoints, bunkers, and buildings at relatively close ranges. The gun was mounted in a limited traverse casemate, meaning it could only swing a few degrees left or right. This limitation actually reduced structural stress on the vehicle. With a maximum elevation of only 20 degrees, it was not designed for indirect fire over long distances, but for direct fire against targets within line of sight, typically under 800 meters. Ammunition storage presented another critical engineering puzzle. In a conventional artillery battery, shells are stored in protected ammunition pits away from the gun. On a self-propelled half-track, every round of ammunition is carried on board, directly within the fighting compartment. This necessitated careful consideration of armor protection and internal layout. The American M12 GMC, for example, could carry only 10 rounds of 155mm ammunition internally, due to the massive size and weight, 95 pounds each, of the shells. These vehicles typically operated in tandem with a dedicated M30 cargo carrier half-track, which followed behind carrying an additional 40 rounds. Similarly, the German Sd.Kfz 251-9 carried 52 rounds of 75mm ammunition, stored in armored bins along the sides of the vehicle where protection was greatest. Anti-aircraft variants pushed the engineering envelope even further. The American M16 multiple-gun motor carriage mounted 450 caliber Browning machine guns in a powered, open-topped turret. This entire system, including the turret, its traverse mechanism, and a dedicated generator, weighed over a ton and was mounted high on the vehicle, raising the center of gravity. Engineers had to carefully calculate weight distribution and sometimes widen the track stance to prevent dangerous rollovers during sharp turns. The combined rate of fire was a staggering 2,400 rounds per minute. However, this consumed ammunition at a prodigious rate. The M16 carried 5,000 rounds in total, which meant its 4 guns could fire continuously for little more than 2 minutes before exhausting its supply. Consequently, a significant portion of the vehicle's interior was dedicated solely to stowing crates of linked ammunition. The ultimate expression of this weapons carrier concept was arguably the German Sd.Kfz 251-22, developed in 1944, which mounted the powerful 75mm PaK-40 anti-tank gun. This weapon was capable of penetrating 100 mm of armor at 1,000 meters, making it a genuine threat to Soviet T-34 tanks. However, mounting such a heavy and potent gun on a light half-track chassis forced severe compromises. Ammunition capacity plummeted to a mere 19 rounds. Armor protection was minimal to avoid overloading the suspension, and firing the gun from anything other than level ground posed a serious risk of tipping the entire vehicle over. Crews of these improvisations learned that their survival depended on firing a single, well-aimed shot and then immediately relocating before the enemy could return fire. The tank destroyer, a weapon of necessity and desperation. The half-track's evolution into a tank destroyer represents military engineering at its most desperate and pragmatic. By 1942, both Allied and Axis forces were confronting enemy tanks that far exceeded pre-war expectations. The Allies faced the formidable German Tiger tank, whose thick armor seemed impervious to most standard anti-tank guns. The Germans, on the other hand, were reeling from the onslaught of the Soviet T-34, which combined sloped armor, good mobility, and a potent gun. In the Pacific, American forces discovered that Japanese tanks, though generally lighter, still required more firepower than infantry rifles or light mortars could provide. The core problem was a matter of time and industrial capacity. Designing, testing, and mass-producing new, purpose-built tank destroyers or tanks was a process that could take years. The stopgap solution was to mount existing high-velocity anti-tank guns onto the readily available half-track chassis, creating an interim vehicle that could be fielded in a matter of months. The American M3 gun motor carriage was a quintessential example of this rush job. Even before the attack on Pearl Harbor, engineers at the Aberdeen Proving Ground took standard M3 half-tracks, removed the infantry benches from the rear compartment, and bolted a 75mm M1897A4 gun, a design dating back to World War I, onto a simple pedestal mount. There was no turret and only a small gun shield for crew protection. The 5-man crew operated the weapon almost completely exposed. Yet, for all its crudeness, it worked. It could penetrate the armor of German Panzer III and early Panzer IV tanks at combat ranges, and between 1941 and 1943, over 2,200 were built. Their baptism of fire came during the North African campaign, particularly at the Battle of Kasserine Pass in February 1943, where American forces received a harsh education in modern armored warfare. The combat performance of the M3 GMC in Tunisia starkly revealed the fundamental vulnerability of the half-track tank destroyer. It could deliver a powerful punch, but it could not withstand one. The vehicle's thin, 6.35mm side armor was barely sufficient to stop rifle bullets and shell fragments, but it offered no protection whatsoever against any dedicated anti-tank weapon or even heavy machine gun fire. German gunners quickly learned to prioritize these vehicles, knowing that a single hit was often sufficient to destroy them. American after-action reports emphasize that to survive, M3 GMC crews had to operate as ambush predators, positioning themselves in concealed locations well behind the front lines, engaging targets at maximum range, and immediately displacing after firing a few shots. They were not meant for head-on duels with enemy armor. The Germans, driven by desperation on the Eastern Front, followed a similar path. Early attempts, like the Sd.Kfz 251 Morten, armed with a 37mm POC 36, were quickly rendered obsolete by the T-34's robust armor. This led to the development of the Sd.Kfz 251-122, which, as mentioned, mounted the excellent 75mm POC 40. While this gun could reliably destroy T-34s, its immense weight, over 3,100 pounds for the gun alone, placed an enormous strain on the half-track's chassis. The vehicle became nose-heavy, its handling cumbersome, and its suspension system was perpetually overstressed. Cross-country performance and top speed suffered significantly. German crews reported that driving a fully loaded Kegresse 251-22 required considerable physical strength and felt like wrestling a stubborn animal, especially in mud or snow. Tactical doctrine for these improvised tank destroyers evolved through bloody experience on both sides. By 1944, American and German manuals emphasized identical principles. Half-track tank destroyers were most effective when used from prepared defensive positions, utilizing natural cover like tree lines or reverse slopes. They would engage approaching enemy armor at the longest possible range, fire a limited volley, and then immediately retreat to a pre-selected alternate firing position before the enemy could pinpoint their location and return fire. Their survival was entirely dependent on their mobility and the element of surprise, as any sustained engagement was almost certainly a death sentence. During the massive Soviet Operation Bagration in the summer of 1944, German Sd.Kfz 251-22s were deployed in small, dispersed groups. They would lie in wait for Soviet tank columns, unleash a sudden, devastating volley from ambush, and then vanish before effective counterfire could be organized. Similarly, in the Normandy hedgerows after D-Day, American M3 GMCs worked in coordination with heavier, purpose-built M10 tank destroyers. The more vulnerable half-tracks would act as spotters or bait, drawing out German armor, which would then be engaged by the more survivable M10s. It was incredibly dangerous duty with high crew casualty rates, but these improvised vehicles played a crucial role in blunting enemy armored assaults during a period when more capable platforms were still in short supply. The half-track tank destroyer was never an ideal solution. It was a necessary one, fielded in large numbers because the alternative was to face enemy panzers with nothing but infantry courage and inadequate handheld weapons. The infantry carrier, the half-track's primary role. Beyond the specialized gun carriers and tank destroyers, the half-track's most profound and enduring impact was in its fundamental role as an armored personnel carrier, APC. Stripped of the guns and the glory, its true purpose was brutally simple: to transport infantry to the battlefield alive, relatively fresh, and ready to fight immediately. While this sounds straightforward, the engineering challenges involved in creating an effective APC represented a delicate and difficult balancing act between three competing and often contradictory requirements: protection, passenger capacity, and overall mobility. Enhancing one characteristic almost always came at the expense of another. The armor scheme of the American M3 half-track is a perfect case study in these calculated compromises. The front plate consisted of 12.7 mm of rolled homogeneous armor steel set at a 30-degree angle. This sloping increased the effective thickness of the armor against incoming fire, providing protection equivalent to about 15 mm of vertical plate. This was sufficient to stop standard German 7.92 mm rifle bullets and 30 caliber machine gun fire at most combat ranges. However, the side armor was drastically reduced to just 6.35 mm. This thin plate could potentially stop pistol rounds and shell splinters, but it was vulnerable to rifle fire at close range and utterly useless against anything larger. The reason for this vulnerability was pure physics. Every additional millimeter of steel armor, spread across the vehicle's large surface area, added hundreds of pounds of weight. The engineers had calculated that 6.35 mm was the absolute minimum required to protect the occupants from the most common battlefield threats, shrapnel and small arms, while keeping the vehicle light enough to retain its crucial off-road mobility. The internal layout was designed with brutal, practical efficiency. The driver and vehicle commander sat in the front cabin, protected by armored doors. Behind them, the main troop compartment measured approximately 6.5 feet in width and 10 feet in length, with two inward-facing bench seats running along the sides. 10 fully equipped infantrymen were packed into this space, sitting knee to knee, their rifles typically held vertically between their legs or laid across their laps. This cramped configuration was intentional. It kept the soldiers' bodies below the level of the armored sidewalls. If a soldier stood up, his head and chest were exposed above the armor, making him instantly vulnerable to sniper fire, machine gun bursts, or airburst artillery shrapnel. Veteran units learned through hard experience to remain seated and low until the very moment of dismounting. The vehicle's open-top design has been the subject of extensive debate. Why not add a roof for greater protection? The reasons were tripartite: weight, visibility, and survivability. A roof made of steel thick enough to provide meaningful protection would have added at least 800 pounds, overstressing the suspension, increasing ground pressure, and degrading performance. More importantly, an enclosed vehicle would have severely restricted the situational awareness of the squad leader and the troops inside. The ability to see and hear the battlefield was a critical tactical advantage, allowing them to react to threats and prepare for dismounting. Finally, in the event of a catastrophic hit from a mine or an artillery shell, an open top provided the crew and passengers with the fastest possible means of escape, a factor that undoubtedly saved countless lives. The true revolution of the half-track, however, was not merely in its engineering but in the new doctrine of mechanized infantry that it enabled. It fundamentally altered the tempo of warfare. Prior to its widespread adoption, infantry either marched, arriving at the battlefield exhausted, or rode in unarmored trucks, which were vulnerable to the slightest enemy opposition. The half-track created a new class of soldier, mechanized infantry that could maintain the same pace as fast-moving tank columns and arrive at the objective with their strength preserved, their weapons ready, and their ammunition dry. This new doctrine was proven during the North African campaign. At the Second Battle of El Alamein in October 1942, British and Commonwealth forces used American-supplied M3 half-tracks to closely follow their armored breakthroughs. The infantry, carried safely inside, could rapidly exploit gaps punched in the German lines, securing key terrain and defensive positions before the enemy could recover. They arrived fresh and combat-ready, able to hold ground that tanks alone could not. The D-Day landings in Normandy on June 6, 1944, provided the ultimate test under extreme combat conditions. American armored infantry divisions used their M3s to push inland from the beaches, carrying troops through the treacherous, close-country bocage hedgerows where tanks were highly vulnerable to ambush. A standard tactical drill evolved. Half-tracks would advance in column behind a spearhead of Sherman tanks, maintaining a distance of 50 to 100 yards. Upon making contact with the enemy, the tanks would provide suppressing fire while the infantry squads rapidly dismounted from the half-tracks, using the vehicles themselves as initial cover. This entire sequence, from first contact to infantry deploying for combat, could be executed in less than 15 seconds. German after-action reports from Normandy frequently commented on the remarkable speed and coordination of American mechanized units, a tempo that their own truck-borne infantry could not hope to match. The scale of this integration is telling. A standard U.S. Armored Infantry battalion in 1944 was organized around its half-tracks. With 3 rifle companies, each containing 3 platoons, and each platoon fielding 4 squads, the battalion required 36 basic personnel carriers alone, plus additional vehicles for command, reconnaissance, and mortar support, totaling roughly 50 half-tracks per battalion. These vehicles were not mere taxis, they were mobile arsenals, carrying the squad's machine guns, mortar rounds, radio equipment, and medical supplies. The half-track had effectively transformed infantry from foot mobile marchers into mounted, combined arms troops, permanently changing the speed, power, and flexibility of land warfare. Adaptation and evolution. The half-track in extreme environments. A machine designed on drafting tables in Cleveland and Stuttgart was destined to face realities for which it was never fully prepared. Deploying the half-track to the brutal Russian winter or the suffocating jungles of the Pacific revealed critical flaws, forcing crews and field mechanics to become innovators, creating ad hoc modifications that the original engineers could never have anticipated. The Eastern Front became a merciless crucible for vehicle design. German Sd.Kfz 251s began suffering catastrophic failures during the terrible winter of 1941-1942 as Army Group Center advanced towards Moscow. The sophisticated interleaved road wheels, so praised for their smooth ride, became a fatal liability. Mud and slush would be thrown up by the tracks, packing solidly into every tiny gap between the wheels and freezing overnight into blocks of ice as hard as granite. crews tried desperate measures, lighting small fires beneath the vehicles, using precious gasoline as a solvent to melt the ice, and even resorting to carefully placed explosive charges. Often, nothing worked reliably. German field workshops responded by welding steel plates over the gaps between the wheels, sacrificing some suspension performance for the sake of survival. By late 1942, this lesson had been incorporated into factory production, with new models featuring simplified suspension with wider wheel spacing. American M3 half-tracks supplied to the Soviet Union via the Lend-Lease program faced different, but equally severe, challenges. The Hercules gasoline engine was not designed for the extreme cold. Carburetors would ice up, and engine oil would congeal into a thick sludge, making cold starts virtually impossible without extensive preheating. Soviet mechanics, renowned for their resourcefulness, implemented field modifications that included installing engine block heaters, insulating fuel lines, and recalibrating carburetors to handle the poor quality, cold-thickened fuel. They also built simple but effective wooden enclosures over the open troop compartments, providing vital protection from the killing wind chill during long transports. Track performance in deep snow demanded radical solutions. The standard rubber block tracks on the M3 would quickly pack with snow, which then compressed into solid ice, destroying traction entirely. Both German and Soviet forces independently developed and deployed grousers, metal cleats that could be bolted onto the outside of the track blocks. These cleats bit into frozen ground and snow like the crampons of a mountaineer, dramatically improving grip. The Germans went a step further, issuing official winter kits that included extended track links, increasing the track's surface area by up to 40% and lowering ground pressure enough to allow traversal of deep snowdrifts that would immobilize any other vehicle. Installing these modifications was a grueling, hours-long task in freezing conditions, but units that neglected this preparation often found themselves completely immobilized within days of a winter offensive. The Pacific Theater presented a diametrically opposed set of hellish conditions. Intense heat, 100% humidity, torrential rain, and dense jungle terrain tested the half-tracks in new ways. The heat and moisture rotted electrical wiring, caused rapid metal corrosion, and turned the steel troop compartments into ovens that could induce heat stroke in minutes. In places like New Guinea and the Solomon Islands, where trails were narrow, ground was soft, and rivers were unbridged, the half-track seemed initially useless. Yet American Marine and Army units again proved adaptable. In an extreme modification, engineers sometimes removed the front wheels entirely from M3s and extended the track run forward, converting them into fully tracked vehicles. These ungainly-looking creations had a much lower ground pressure and could navigate swamps and deep mud that would stop any other vehicle. Japanese forces, when they first encountered American half-tracks in the Philippines, were often perplexed by them. Their own military doctrine favored light tanks and simple, unarmored trucks, and they viewed the half-track as an over-engineered and maintenance-heavy compromise. In the context of the resource-starved Japanese military and the tropical environment, they were not entirely wrong. The complex mechanical systems of both American and German half-tracks suffered terribly in the jungle. Humidity corroded electrical contacts, organic mud clogged radiators and fouled bearings, and the vehicles required constant, meticulous maintenance to remain operational. The story of captured vehicles provides some of the most fascinating examples of adaptation. The Soviet Red Army captured hundreds of German Sd.Kfz Tu-51s during their great offensives of 1943, 1944, and immediately pressed them into service. Facing shortages of original German ammunition and parts, Soviet workshops heavily modified these prizes. They welded on additional armor plates scavenged from destroyed T-34s, creating heavier, slower, but better protected hybrids. Some captured Hanemags were rearmed with Soviet 82mm recoilless rifles, Katyusha rocket rails, or even flamethrowers, creations that would have horrified their original German designers, but perfectly suited the Soviet preference for maximum, practical firepower. Japanese forces, when they first encountered American half-tracks in the Philippines, were often perplexed by them. Their own military doctrine favored light tanks and simple, unarmored trucks, and they viewed the half-track as an over-engineered and maintenance-heavy compromise. In the context of the resource-starved Japanese military and the tropical environment, they were not entirely wrong. The complex mechanical systems of both American and German half-tracks suffered terribly in the jungle. Humidity corroded electrical contacts, organic mud clogged radiators and fouled bearings, and the vehicles required constant, meticulous maintenance to remain operational. The story of captured vehicles provides some of the most fascinating examples of adaptation. The Soviet Red Army captured hundreds of German Sd.Kfz 251s during their great offensives of 1943, 1944, and immediately pressed them into service. Facing shortages of original German ammunition and parts, Soviet workshops heavily modified these prizes. They welded on additional armor plates scavenged from destroyed T-34s, creating heavier, slower, but better protected hybrids. Some captured Hanemags were rearmed with Soviet 82mm recoilless rifles, Katyusha rocket rails, or even flamethrowers, creations that would have horrified their original German designers but perfectly suited the Soviet preference for maximum practical firepower. Desert warfare in North Africa required yet another distinct set of modifications. Fine, abrasive sand infiltrated every moving part, causing engines to wear out in a fraction of their normal lifespan. British forces using American M3s in the Western Desert Campaign installed enormous, oversized air filters, some standing 3 feet tall, to prevent sand from destroying the engines. They also swapped the standard tracks for special desert pattern tracks with wider rubber blocks that provided better flotation in soft sand. The scarcity of water was another critical factor. Half-tracks operating in the Sahara often carried extra coolant and towed trailers loaded with nothing but water cans, essential for both the vehicle's radiator and the survival of the crew. The overarching lesson from these global deployments is that the half-track was not a single static design. It was a platform that spawned dozens of localized variants, each evolved through brutal necessity to survive in specific environmental hells that would have quickly destroyed the original factory-fresh vehicle.